morning, dear students. Welcome back. I am your physics professor, Dr. Nagaraj. So I am here to teach you engineering physics for electrical and electronics engineer stream, module number 4, which is nothing but Maxwell's equations and electromagnetic waves. Dear students, many students are asking me to revise the syllabus, but time is very short. I have already done some revisions and also some model paper discussions. The videos are available in my channel. Please go to that particular video and watch it. And examinations are at the corner, so they are fast approaching. So concentrate more on the previous year question paper and also whatever your teacher taught in your regular class. Also, please refer your internal test question papers. So 2 tests, in some colleges there might be 3 tests also, so they might have done. Please go through all those things. Well, now with this brief introduction, let me come to the actual portion, Maxwell's equations and electromagnetic waves. Dear students, Maxwell's equations are very essential for communication purpose. Maxwell has written 4 famous equations, and these equations are totally based upon electrostatics, electromagnetism, okay, and current electricity. And these 4 equations are so important that Richard Feynman, you might have heard of this person name, has called this particular achievement as one of the significant achievement of 19th century. Maxwell wrote these equations in 1870, and also Boltzmann called Maxwell's equations as God's own equations. I think these 2 statements are enough to show the importance of Maxwell's equations. Maxwell's equations are important achievement of 19th century and God's own equations. Only 4 equations, and actually derivation part of these equations is not there in the syllabus, but in your higher semesters, maybe in 4th semester, you will study engineering electrodynamics. There you will electromagnetics or electrodynamics. You will study electrodynamics in 4th semester, electromagnetics in 4th semester, and there your teachers will derive those equations. And I have written one book also for this particular topic, electromagnetic field theory and electromagnetic waves. It is available in market. Okay, now come back to this particular topic. It is perfect mixture of physics and vector calculus. So you need solid background of vectors, vector calculus, vector algebra, and also physics. Well, without spending much time, let me directly start with vector. Dear students, you know what is a vector? Vector is nothing but a quantity having both magnitude and direction. We represent vector by various ways. The easiest way is by writing a letter with arrow mark. In some textbooks they write it as in bold letter, but bold letter we can only consider in print form. While writing, it is not possible to write bold letter. This is the most convenient method. If you have arrow mark over there, it is vector. Without arrow mark, it is scalar. And vector has got magnitude as well as direction. Therefore, we write it as modulus of A and A cap, where A cap represents unit vector. There are different types of vectors, and already you have enough knowledge of fundamentals of vectors. Okay, and magnitude, or okay, any vector, for example, vector A is represented in terms of x, y, z coordinates. Okay, x I cap plus y j cap plus z k cap. Here I, j, k are the unit vectors along x axis. This is x axis unit vector. This is y axis unit vector. This is z axis unit vector. So z axis, x axis, y axis. Cartesian coordinate. Maybe in your higher semesters you will come across with other coordinate system also, like polar coordinate, cylindrical coordinate, okay, all those things. But for us, Cartesian coordinate, where we measure x, y, z only, means all the 3 are linear parameters are enough. Okay, and to find the magnitude of A, we need to find what is called, that is modulus of A is nothing but root of x square plus y square plus z square. I think you know all these things. PUC only you studied these things. And here x, y, z are called coordinates. At any point, if you have said in the coordinate system, you have a point here, the line joining the point to the origin is called position vector. It is characterized by x, y, z. Okay, so vector P or vector A is nothing but position vector. Now these vectors can be added, can be subtracted, can be multiplied. Addition and subtraction not required for me. I go directly with the multiplication. There are 2 types of multiplications. One is dot product, another one is cross product. Dot product is nothing but modulus of A modulus of B into cos theta. Cross product is modulus of A modulus of B into sin theta. Even this is also very basic. You studied this in PU. Dot product is also called a scalar product because it is going to end up in scalar quantity. Best example is work done. Work done is equal to force into displacement, that is F dot S, that is Fs cos theta. Here F is a vector, S is a vector, force is a vector, displacement is a vector, but work done is a scalar. Next, cross product is also called as vector product because it is finally end up in vector quantity. For example, force acting on a charged particle, it is Q into V cross B, that is a B Q V sin theta, force acting on a charged particle placed in the magnetic field. You can give many examples for dot product and cross product. And one more thing regarding dot product and cross product, I write it here only. I dot I is equal to 1. Similarly, J dot J also, K dot K also, because I dot I theta 0 cos 0 is 1. Okay, suppose if you go for I dot J, it is 0. Why? Because I dot J angle is 90 degree, cos 90 is 0. That means like vectors you can, like means like direction, same direction, we can take the dot product. It is not going to be 0, it is going to be maximum. Perpendicular vectors, it is 0, dot product. When it comes to cross product, I cross I equal to 0 because I and I having angle 0, sin 0 is 0, so cross product of same vector is 0. Whereas I cross J is equal to K. Okay, these are all very basics, and for me these things are required to go ahead with the remaining part of this chapter. That's why I have given some introduction. But dear students, don't expect any questions from these things. It is only to march ahead in the chapter. Well, with this I move on to the next part. Our actual discussion starts here. Vector we know, scalar we know. What is scalar field, what is vector field? So that is our next heading. So let me now explain what is scalar field. See, scalar quantity, best example is temperature. We can have many examples for scalar: temperature, pressure, mass, time, length, all these are scalar quantities only. Vector, when it comes to vector, velocity is the best example for vector. Now in this room I have temperature. Okay, temperature exists everywhere. Now you take one thermometer, put it here and look at the reading. It will show some value, let us say 27 degrees centigrade. So here temperature is 27 degrees Celsius. Don't ask me whether it is in this direction, this direction, this direction, because there is no meaning for direction of the temperature. That is the meaning of scalar quantity. Okay, in this room I have temperature. Let us somewhere here I have temperature. This point is having only magnitude, that is 27 degrees centigrade. Somewhere here if I measure, there it may be 27, it may be 27.5, but definitely there will be temperature. Like this, in this room everywhere I can have points like this. Each point corresponds to one particular value of temperature. Each point represents one scalar quantity. So that point is called point function. So what is point function? Point function is a point associated with one physical quantity. If that physical quantity is a scalar, we call that point as a scalar point function. So everywhere in this room I have temperature. Everywhere in this room I have humidity. Everywhere I have in this room pressure. Suppose if I lit one incense stick, agarbatti, okay, or if I spray room spray freshener, everywhere there will be fragrance. Okay, so that means in this room each and every point corresponds to some measurable quantity. Okay, each and every point corresponds to point function. Okay, and if the point functions are continuous, that entire region is known as field. Please remember, field is nothing but continuous distribution of point functions. Continuous distribution. Everywhere I should have temperature, everywhere I should have pressure, everywhere I should have fragrance, everywhere I should have light. If I lit the light, light bulb, light spreads in the room. It is not that I have light up till here, afterwards discontinuous darkness, again light starts. It is not so. Of course, it may be possible if I put some opaque object. If I put dark screen here, up till here there is light, then onwards no light. That is discontinuity. But that I cannot call as continuous field. If I remove the obstacle, everywhere there is light. So that is light field. If I lit the fire, everywhere there will be temperature. That is thermal field. If I spray the room freshener, everywhere there is fragrance. That is perfume field. Or if I lit the agarbatti, everywhere there will be fragrance. Or if I allow water to flow in the river everywhere there is water flow. It means there is velocity. Like that. Or if I have a point charge, everywhere there is electric field. If I have a charged particle, everywhere there is a electric field. Got it or not? So this way, field is nothing but continuous distribution of points. So now comes the definition. Point function is a point where there is a physical quantity. If the points are continuous, it is nothing but field. If the point represents a scalar quantity, it is called scalar field. If the point represents vector quantity, then it is called vector field. For example, around a charged body, I have force. I have force everywhere. Each point corresponds to force. Suppose if the water is flowing like this, here I have a velocity, here I have velocity, everywhere I can draw the velocity. So each point represents both magnitude and direction, so it is vector field. I hope you got it. So scalar field, vector field. Field is nothing but continuous distribution of points. If the points represent scalar quantity, it is scalar field. If the points represents vector quantity, it is vector field. Now scalar field is associated with what is called spherical surfaces, spheres, zones. Zone, like for example, I have a fire here, very close to the fire, at a distance of 1 meter, 1 meter, 1 meter, 1 meter, I have high temperature. Okay, so around this fire 1 meter circle, 1 meter zone, more temperature. I move little bit farther, 2 meter, there will be lesser temperature. Like that, as I go away from the fire, temperature will be decreasing. So that is characterized by what is called zone or spheres. Similarly, vector field is characterized by arrow marks. So zones are the characteristics of field, scalar field. Arrow marks are the characteristics of vector field. Please recall the charge only. Around the charge we draw zones. They are nothing but equipotential surfaces. You know, potential is a scalar quantity. Everywhere on the surface potential is same. Everywhere on the surface potential is same. Everywhere on the surface potential is same. Okay, so these are equipotential surfaces, and electric field like this. So field is characterized by arrow marks. So in this diagram I have expressed both vector field as well as scalar field, and also zones as well as arrow marks. So now you know what is scalar field, what is vector field, how to represent them. Right, now in order to understand the variation of these fields, whether it is scalar field or vector field, they continuously vary. For example, temperature. Just now I gave an example. From the fire, if you move away, temperature decreases. Or from the charge, if you move away, electric field decreases. Like this, the field where parameters are subjected to vary. Electric field varies, magnetic field varies, thermal field varies. All the parameters are going to vary. Now, these variations we can understand, these changes we can understand through what is called vector calculus. In order to study the variation in the fields, we need the support of vector calculus. In vector calculus, we consider an important parameter called del operator. So this is very important. Del operator. Okay, del operator is the next heading. Well, I so far gave introduction to vectors, concept of field, point function, and then scalar field and vector field, and how to represent, and example. Potential is vector field, electric field is scalar field. That is sufficient for us right now. And to know the variation of the field parameters, we need the support of del operator. What is this del operator? Listen carefully. First I take one example. Best example, hot iron sphere. I have hot iron sphere over here, right? Very hot, red hot iron sphere. And if you move away along x-axis or along y-axis or along z-axis, definitely temperature decreases. Around the sphere it is very hot. As you move away, it keeps on reducing. Maybe far away from the iron sphere, it will be nominal. Okay. Now I will ask you one question. Well, along x-axis, y-axis, z-axis, or okay, let me take this, x-axis, y-axis, z-axis. Tell me, as you move along x-axis, temperature decreases. The question, whether decrease in the temperature along x-axis, does it depend upon the parameter along y-axis? No. That means, what I mean to say, let us consider two boys, x boy, y boy. X is sitting here, y is sitting here. When x move away, what happens? He will feel less heat. What happens to y? He will not feel less heat. He will feel same heat. Change is only happening for x, not for y. That's what I said. That means variation in the temperature along x-axis does not depend on y-axis, does not depend on z-axis. Similarly, variation along y-axis does not depend on x and z. Similarly, variation along z-axis does not depend upon x and y. I hope you got it. Well, with this, now I write one equation. Follow carefully. Total change in the temperature as you move away is equal to change in the temperature along x-axis. This is called dou t by dou x, partial differentiation, into dx, right? I write only 2 coordinates. It is applicable even for 3 coordinates also. Or okay, I will write 3 coordinates only. Plus changes along y-axis, that is dou t by dou y into dy, plus now I think you can guess the third term. Yes, you are correct. Dou t by dou z into dz. Correct? Well, this is dt. This is the total variation, the temperature. Now I rewrite it as dt is equal to, follow carefully, dou by dou xi plus dou by dou z, dou by j plus dou by dou zk, right, multiplied by t dot, I continue here, dxi plus dyj plus dzk. Please follow carefully. If you simplify this, you will get back the same equation. You know how? As I already told, that's why I told this one in the beginning. I dot I is equal to 1. That means I should multiply only I and I, y and y. That means I and I, j and j, k and k. So dou t by dou x into dx. Dou t by dou y into dy, j into j, 1. Okay. Dou t by dou z into k, that is dou t by dou z into dz. So when I simplify this, I get back the same answer. Okay. Well, that is not my thing. My intention is to explain this parameter. This one I write as del. This whole thing I write as del into t dot. This whole thing I write as position vector. Okay. Now see, this is a dot product. Dot product means it must be 2 vectors. Yes, this is a vector then. This is a vector. But dear students, I already told you temperature is a scalar. Therefore, when I put arrow mark, I am putting the arrow mark on del. So del is a vector here. So del is a vector which is nothing but dou by dou x I cap. Even sometimes I will ignore I cap, but still it is there. It is representing direction. Dou by dou y j cap plus dou by dou z k cap, called del operator. What is this del operator? Del operator is one of the important operator in vector calculus. It represents differentiation. What is the difference between differentiation and del operator? The main difference is normal differentiation. See, in mathematics we have so many operators, like integration is an operator, addition is an operator, division is an operator, sigma is an operator, minus is an operator, like this. Even d by dx is an operator. Del is a differential operator. But the difference is, there in normal differentiation d by dx or dou by dou x or d by dx, we consider only differentiation of the magnitude. But here it is not only magnitude, even direction also. Remember, we are not talking about ordinary calculus. We are talking about vector calculus. So vector calculus means not only magnitude calculus, even direction also. So you differentiate even direction also. When you differentiate direction, you must have this del operator. So del operator is equivalent to differentiation operator with one difference. It is having a directional parameter also. Hence it is not only magnitude, also direction. Hence it is vector operator. So del operator is a vector operator equivalent to differentiation, and it is given by this symbol, this equation, and this is the symbol. Some specialities are del can operate on scalar quantity, can operate even on vector quantity also. That I will come to next. That means I can operate del on the scalar field, also in the vector field. Second, del is not operated by some parameters. Del cannot be operated by someone. It is going to operate on someone. That means, let us say I have some function multiplied by del, there is no meaning. Del operating on function, there is a meaning. I give you one example, like a differentiation d by dx of 2x square. This is meaningful. That means differentiate 2x square. Yes, we know it is nothing but 4x. Can you have problem like this 2x square into d by dx? Have you ever seen this type of problem? No sir, we have not come across with this type of problem. That means differentiation is operated by a function. Differentiation is going to operate on function. This is what your mathematics teachers might have told in the regular class. Similarly, del is not operated by someone. Del is going to operate on someone. Therefore, these two are not same. This is actually meaningless. This is only having meaning. Now, I said del can operate on both scalars and vectors. So, del can be multiplied with scalar and vector. How to multiply? Based on this, we have three parameters known as divergence, gradient and curl. Okay, I start with gradient and then divergence and curl. So now like next heading is the gradient, divergence and curl. See here the whole discussion, vector, concept of field and then del operator. In field we have scalar field and vector field. Okay, and when it comes to vector field especially, we have two parameters, namely circulation and then flux. See, field, this is field, okay, this is field, something coming out, this is field, vector field. Or I have a straight conductor carrying current, around this I have vector rotating like this also, swirling, that is magnetic field produced around the current carrying conductor. Okay, Biot-Savart, thumb rule, etc. This is current, this is magnetic field. Look at these two, this is also field, this is also field, this is a vector field, this is also vector field. Here, in this case, something is coming out, okay, from the pipe water is coming, or here something is rotating. So this is three-dimensional, this is two-dimensional, this is three-dimensional, this is two-dimensional. In three-dimensional, something is coming, something is getting, there I talk about flux. In two dimensions, something is rotating, either clockwise rotation or anti-clockwise rotation, there I talk about circulation. And for the definition's sake, circulation is defined as integral of vector and then line or small element. Okay, tangential. See this is the rotation. So I draw the tangent here, I draw the tangent here, the vector and that particular length. So it is tangent and particular length, circulation. Flux is not like that. Please recall electrostatics in PUC, number of lines coming out over surface area. Number of lines coming out means normal, number of lines passing through the surface. So therefore flux is integral of normal component, velocity or electric field or whatever it is. Here it is tangential component, here it is normal component. In the curl it is tangential, in the flux it is normal, something which is passing through, not passing, grazing, not on the surface. On the surface it is through the surface. Therefore it must be V dot ds. See the difference between the two. This is tangential component and length. This is normal component and surface. Okay na? So these two things are very important in understanding gradient, divergence and then curl. Okay, I will proceed with those three parameters. Okay, now comes divergence, gradient. Okay, now comes gradient. See, I told you del can operate on scalar as well as vector. In subsequent discussions, sometimes I take T for scalar, H for vector. Okay, so now gradient. How do you define gradient? If del is directly operating on a scalar quantity, see temperature is a scalar quantity, then we call it as gradient. So gradient is equal to del multiplied on a scalar. So del of a scalar is gradient. Okay, so gradient is direct multiplication. Remember, del is a vector, T is a scalar. When vector is multiplied on scalar, it is going to be a vector quantity. What I mean to say, gradient is a vector quantity. Define grad. Grad of a function f is equal to del of f. It is a vector. Even though this is a scalar, overall it is a vector. What actually gradient represent? Gradient represents the variation of the scalar quantity in a particular direction. For example, you have a red hot iron sphere. As you move away from the sphere, temperature decreases gradually. That word grad comes from gradual. Okay, and del T can be positive, can be negative, can be zero. Can be zero means there is no change. Positive means field is increasing, negative means field is decreasing, and gradient has got meaning only when it is operated on a scalar. That means there is no meaning for gradient of a vector. Gradient of a vector does not carry any meaning. And I said the gradient is a vector, so magnitude is given by this formula and the value. Okay, you can expand del, you know, del is nothing but dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap multiplied by t. This is the gradient, and the direction is always along the increasing temperature. If del is positive, along increasing the value of temperature. Negative means along decreasing value of temperature. For example, if you have a charge over here, as you move away from the charge, potential keeps on decreasing. Here it may be 10 volt, here may be 5 volt, here may be 3 volt. So as you move away, potential decreases. In fact, dV by dx athwa del V is nothing but electric intensity with negative sign. So here negative sign represents electric intensity is along the decreasing direction of the potential. Potential is not a vector. Potential decreases, in that direction electric field is acting. So electric field is nothing but negative potential gradient. So gradient bagge you can write these many parameters. Gradient of a scalar is nothing but del of f. It is vector and it is always in the direction of increasing field. Positive, negative means decreasing, zero means no change, and there is no meaning for gradient of a vector. So this is simple multiplication. Now comes another quantity, divergence. Divergence is nothing but dot product of, when I say dot product, there must be two vectors, so it is del dot h. I told you, h is vector here, like t is scalar, h is vector over here. So it is del dot h. It is a dot product. Okay, that is equal to dou by dou x I plus dou by dou y j plus dou by dou z k dot h means xi plus yj plus zk. When you take the dot product of this, it is going to be a scalar quantity only. That means divergence is a scalar, gradient is a vector, divergence is a scalar. Divergence can be positive, can be negative, can be zero. Positive means outward flux, negative means inward. That means from a point, if the flux is diverging like this point can be called as a source. Suppose if the flux is converging at a point, we call this as a sink. Positive means source, negative means sink. Zero means what? Suppose if the number of lines entering at a point is equal to number of lines leaving at a point, then the total flux is zero, divergence is zero. In that case, we call this as solenoidal. So if divergence is zero, we call it as solenoidal. It is also called as incompressible. So this is about divergence. See, here also I have del, here also I have del. Divergence means it is a dot product, gradient means it is simply product. Okay, well, some specialities. Divergence is always taken for a vector. There is no meaning for divergence of a scalar. Even though final answer is scalar, we never write del dot scalar quantity, because a dot product is always between two vectors. Divergence can be positive, can be negative, can be zero also. Divergence means from the point the flux is coming, so that point is source. Like from the point water is coming out, from the positive charge field is coming out, like that. Flux is coming out, like that. And if the total flux is zero, it is called a solenoidal or incompressible. This is about divergence. And next, finally, curl. Another parameter is curl. See here, I simply multiplied. Here I took the dot product. Now I am going for cross product. So define divergence. Divergence is the dot product of del and a vector. Curl is the cross product of del operator and a vector. Curl represents circulation, rotational effect. Curly hair you might have heard of, no? So curl means something which is rotating. Divergence means something which is coming out or getting in. Okay, there it is something like flux. I told you in the few minutes back. So divergence is associated with flux, curl is associated with rotation or circulation. And this curl is calculated, of course it is a vector quantity. So nodi, this is a vector quantity, this is a scalar quantity, this is again a vector quantity. This is ordinary multiplication, this is dot product, this is cross product. And how do you find out the curl? Yes, it is using matrix determinants formula, IJK and dou by dou x, dou by dou y, dou by dou z. This is x, y, z, and I hope you all know how to simplify this matrix. It is a 3 by 3 matrix. Okay, so this is curl. Okay, something about curl. Curl can be positive, that is clockwise rotation, can be negative, anti-clockwise rotation. Zero means irrotational. If the divergence is zero, we call it as solenoidal. If curl is zero, we call it as irrotational. Best example for curl, a straight conductor carrying current, magnetic field produced around it is the best example. Best example for divergence, electric flux, magnetic flux also, but I take electric flux because it is more convincing and convenient. Okay, now coming to significance of curl. As I told, curl represents rotational effect. Curl is positive for clockwise, negative for anti-clockwise, zero for irrotational. Okay, and curl is always for vector, not for a scalar. It is a cross product. And finally, we have two more definitions for curl and divergence. Please remember these equations. Divergence is also written as surface integral of vector h dot ds divided by v when limit of v tends to 0. This is another definition, but definition alla idu, better you take it as an equation. Divergence, that is del dot h, is also given as limit of integral of h dot ds divided by by V as V tends to 0. The surface integral, this is called surface integral. Similarly, for curl we have an equation that is del cross H or del cross B del cross E, that is equal to limit of line integral of H only, okay, I have taken H dot dl divided by S or ds when ds tends to 0. Please remember these two equations. Here divergence is nothing but limit of surface integral divided by volume. Curl is nothing but limit of line integral divided by volume. Dear students, I am using two words here, surface integral, line integral. If integration is over a surface, means if you have ds here, it is surface integration. If it is only on a line, it is line integration. Like for example, I have a line, single line like this. I divide this into different parts, and then I keep on adding dl like that. Then it is line integration. Instead of that, I have a full surface. I divide that into different segments, like around the charged body. I have a full surface. I integrate over here, I integrate over here, I integrate over here. Then it is surface integration. Similarly, if we have overall volume, then it is called volume integration. So we have three types of integration: surface integration, line integration, and volume integration. So I have explained three things: gradient, divergence, and curl. Now with this, it is time to move on to one important derivation of this chapter, that is Gauss divergence theorem. Gauss divergence theorem I will explain now, and then I will end the video. The statement surface integration of flux of a vector field is equal to volume integration of divergence of that vector. See, flux of the vector E dot ds is equal to divergence of the vector del dot E. This is surface integration, so I have ds here. This is volume integration, I have dv over here. So prove this. This is one of the expected questions. State and prove Gauss divergence theorem. Statement: surface integration of a flux is equal to volume integration of the divergence. Okay, it goes like this. Let me consider a charged body inside. It is surrounded by some imaginary boundary. This boundary I divide into different parts. Okay, this is a three-dimensional boundary. I divide into different parts. So electric lines or flux is coming out. Okay, lines of forces are like this. Well, I assume that electric field is constant and it is divided into different segments. Then the total flux integral of E dot ds is equal to, it is E dot ds1, that means over one small portion, plus integral of E dot ds2 over another portion, plus etc. That means this is equal to sigma of integral of E dot ds. Are you following? Yes, this can be written as sigma integral of E dot ds multiplied by V divided by V. Okay, so that is equal to sigma integral of E dot ds divided by V, whole thing multiplied by V. Look at this equation: E dot ds divided by V, H dot ds divided by V. It is nothing but a divergence. So therefore I can write this as sigma. Okay, this entire thing is nothing but del dot H multiplied by V. Okay, now I continue here. This is equal to sigma, put sigma V is equal to integral of dV. Put sigma V is equal to integral of dV, so that this becomes, okay, I write here, this becomes, so surface integral of E dot ds is equal to, so this sigma V I have written as integral of dV, integral of, okay, del dot H. Del dot H means here del dot E into dV. Okay, I write this once again. That is equal to integral of del dot E into dV. This derivation I have given in the notes. Notes link is available in the description box. Please go through this derivation. Very simple. I divide this into different segments. I add it, then I total it, that is sigma, then multiply by V divided by V, and then this you rearrange. This whole thing is nothing but del dot E, that is nothing but divergence, and then sigma V I take it as integral of dV. So So then sigma v integral of dv I merge with this. Okay, so surface integral of E dot ds is equal to volume integral of divergence of the vector. This is divergence theorem. Dear students, I will come back to you with few more concepts, maybe another 1 or 2 videos I will do. Also I will share you numerical problems, solved numerical problems video I will do and I will share with you. Okay, thank you for your constant support.